We'll watch a video next time about capacitors, but I know you don't want to cover this test. I gave you an expression for the capacitance, that whole epsilon naught A over D. The epsilon naught is in the back on your equation sheet. So if you're looking for the epsilon naught, is this value? It's on your equation sheet. Goodness, bless you. All right, let's do about 15 more seconds or so. Goodness, bless you. All right, I'm going to stop at 2:15. 2:15. All right, B is right, I'm pretty sure. We do C equals kappa, epsilon naught, A over D. Put in those values. Kappa is 1.5. Epsilon naught, I think, is 8.85 times 10 to the minus 11. Am I right about that? That's right? 12, okay. Factor it in. All right, A is 0.4. And then the separation between them, they're usually pretty close together. It's about a micron on these. And that gives me 5.3. Was it 5.3 B? Times 10 to the minus 6 farads are micro. Make sure you know your micro. On this exam, too, we'll see a lot of that for capacitors. Okie dokie? All right. Listen, I know some of you have discovered that these questions, these are just from old tests, right? So you can look up the answers if you want, even on your phone or whatever. But that sort of defeats the purpose, because the purpose of the questions are for you to practice in class, sort of to see questions without having the answers in front of you. And so it sort of defeats the purpose. If you answer all the questions in class, you're going to get your full class participation. Very few people actually don't get their full participation. So I encourage you to just sort of try these questions blindly. All right, let's look at the test. I will just sort of give you a brief overview of what you're going to see on the test, though I think many of you know. And then if you have questions, we can look through some of the old exams, and if you have particular questions, then we can look at those as well. The test will be in the auditorium. You will have a seating chart out in that little lounge area. And so find your seat and go sit there and, you know, wait for your exam. Try to get there a few minutes early. All right, so you're going to see some just basic charge stuff. So sort of the properties of charge. That's going to include things like quantization of charge, conservation of charge. Quantization meaning, you know, charge comes... Quantization. Charge comes in particular quantities. Also, charge is conserved. Charge, you get opposites attract, likes repel, opposites, likes. Go over that part of the chapter, just reminding yourself of the basic properties of charge. Charging by conduction and induction. knowing what those are. Conduction requires contact between two surfaces. Induction does not. So just those basic properties of charge. Then we get into things like Coulomb's law and forces. You're going to see both quantitative and qualitative. Quantitative means, calculate the force, calculate the charge if I give you a force, or calculate the distance between these objects. We've had questions like that, but you'll see some on Monday like that as well. And then qualitative in the sense of, if I have this configuration of charges, in what direction is the force on this charge? We've done those, where I give you a selection of arrows and you pick the right one. Or I give you the direction of the arrow and you pick the right charge configuration that gives you that. Remembering that opposite charges attract, like charges repel. But you also need to know how these vectors add up when you're thinking about them conceptually in your mind. We've done that a bunch, so I think that y'all are okay. But if you're not, let me know. We can spend some time Monday morning or this afternoon going over it. All right, so quantitative and qualitative. You will have some 2D vector problems. It may or may not involve forces. It could be electric fields, but you will have 2D, where I ask you the magnitude and the direction of either an electric field or an electric force. So be ready for that. They're not real complicated. I try to make, let's take that back. I try to make the math as easy as possible for you, so that you're not dealing with a lot of funky numbers, okay? But you will have to deal with 2D vectors. You need to know what electric field is. Several things for the electric field. You need to be able to relate the field to the force. Remember, the force is equal to Q times E. In fact, that's how we define electric field, that an electric field is a force per unit charge. At its very basic level, that's what a field is. It's a force per unit something. You could have some basic kinematics. So remember, your basic kinematics equations. Those aren't on your equation sheet, but I think that y'all know them. If you use them, it's going to be like a one-step kinematics problem, like what we've done in class. You have some in your homework like that as well. So you can find the acceleration if you know the force, and then you can use that to figure out the velocity or the position of a particle after a certain amount of time. You need to do some qualitative stuff with electric fields. So we've done some of these things where, like, for example, I give you a configuration of charges and I ask you, where's the electric field equal to 0? Where can I put a particle and it will feel 0 force? We've done those in class, so make sure that you're good on those and that you can think about, where is the electric field or in what direction is the electric field, kind of like what we had with Coulomb's law. We can look at some questions like that in just a moment if you're unclear. And then you also need to know how to do field lines. Remember, these are related to the direction and then also the density of the lines. So a couple of things. You need to know that the direction of the field lines running from positive to negative. So if I have a positive charge, a negative charge, my field lines will go like that. If I have twice the charge here, I'm going to have twice as many field lines. So be able to determine the sign and the magnitude of the charge like we've done in class. And on the homework as well. Also know equal potential lines. Equal potential lines, remember, let's see here, run perpendicular, that's this word, run perpendicular to the electric field lines. Know that relationship. Equal potential lines are always perpendicular to the electric field lines. I think that's it for that chapter. And then we move into the potential. So regarding potential, remember guys, we're dealing with 3 big ideas. We're dealing with forces, we're dealing with electric fields, which are force per charge, and we're dealing with energy per charge, which is our potential. So this is forces, this is electric fields, and this is our potential. Also remember that those equations, they all look very similar. So try to keep them straight in your head. F equals K QQ over R squared. E equals KQ over R squared. V equals KQ over R. And then we also have this potential energy. All right, don't get it confused with potential. It's a little bit different. It is KQQ over R. As I told you in class the other day, these are both vectors. These are both scalars. And so you treat them differently. If I'm dealing with vectors, you know I have to deal with vectors. I got to do all the business that you do with vectors. But when I'm dealing with scalars, I just add them up like numbers. But remember, there was something that had to do with when you're calculating these. How are these different, these two sets of equations? How do I treat them differently when I'm actually doing the calculations? I keep the signs. Which one, the top or the bottom? I keep the negatives. The bottom. Yeah, so in the bottom. Here, you don't include the negatives. In fact, if you look in your equation sheet, you got little absolute value bars around these Q's to remind you of that. But on the bottom, you keep those negatives. A negative potential, that doesn't refer to direction. It refers to like a difference in energy. All right? So potential is energy per charge. You need to understand those basic ideas about potential, that it is energy per charge. Remember that positive charges move from high to low potential, and negative charges just do the opposite. So I gave y'all this sort of analogy that a positive charge on a mountain will roll downhill. It moves from high to low potential. It's a similar idea, actually. Now, you need to know how to do the potential of point charges. You'll have 2 to 3 point charges, and you just have to find the potential of those point charges. So if I have, say, 2 point charges at this point, if I want to know V of it, and this is Q1, this is Q2, I just determine V equals KQ over R for both of them, and I add them up. An arithmetic sum, not a vector sum. I just add those numbers up. You need to understand the relationship, and this is in your equation sheet, and it came up in your homework. We didn't talk about it a whole lot in class, but it came up in your OpenStax assignment. The relationship between voltage, or potential, and the electric field. All right. This came up in your assignment this due tonight, and then also in your reading due a few days ago. There is a relationship between our potential and our electric field that's related to the distance. And it's kind of important for you guys because you talk about cells and the charges and how they transfer between the different places in a cell. So remember this. This relationship is on your equation sheet, but just be aware of it. You can think of this in terms of units too. If I just look at the units, this is V in volts. This was volts per meter, and then this is meters. Remember we had 2 sets of units for electric field? We had newtons per Coulomb, but then I also said that you can also measure them in volts per meter. All right, I think that comes up on your assignment tonight. And electric potential. So if I have a set of 3 particles, and I want to know they have potential energy contained in that set of 3 particles, if I want to know the total potential energy, I add up U equals KQQ over R for all 3 sets of particles. So I'd calculate KQQ over R for those 2 particles, and for those 2 particles, and add them all up. If you had a homework problem related to that, if it's just 2 particles, it's real easy. You just have 2 particles to consider. If you have 3 particles, you have 3 distinct pairs. Each of them contain their own potential energy because of the way they interact with one another, and so you have to add them all up. Remember, if you have a negative charge, you include the negative here. So that negative charge would actually take away energy from the configuration. And I think that's it as far as the topics. I recommend that you go over the old test, go through the homework, go over your notes, and then also remember that I pull, I don't know, 4 maybe? I think I pulled 4 questions from your OpenStax assignment. Not your personalized questions, and not the real wonky questions, but the questions that are similar to ones that we've covered in class. So I would go through and look at those OpenStats, just review them. They have, feedback for you. That's right? They sort of give feedback for the answers. Yes, okay. Yeah, they sort of give you a brief synopsis of how to work it. But if you have questions about it, then please let me know. Send me a screenshot or whatever. So, you want to look at some old exams, or y'all have particular questions about old exams? I think you'll have S16, Spring 16 in the back. So if y'all want to look at that, we can. I don't think we actually haven't worked that much of that one. I'm just going to sort of scroll through here. The first part of this, your test will be laid out in the order of the topics. They'll be sort of grouped by topics. But this first part has to do with, basic properties of charges. You'll see 4 or 5 questions of that. Here is a Coulomb's law problem. You could have it either in 1 dimension or 2 dimension. I think we might have worked this problem. It actually works out to be a 1-dimensional problem. The direction. Some stuff like this, if I change a variable, what happens to the other variables? Here, what are the charges on these? You count the number of field lines. Remember, count the field lines. Take the ratio. It's the magnitude of the electric field. There's a 2D problem. I'm just sort of giving you a brief survey, but y'all holler out. Here's a kinematics problem. Some of these qualitative things regarding electric fields, number 14. Number 13, this sort of basic idea of what is a field. See a similar question for what is a potential. Yeah, China. 15? Mm-hmm. Yeah, so 15, be something similar to this. This asks for the velocity. I could also ask you for the position. But the main thing that I'm really looking for is that you're able to take the electric field and determine the force. F is equal to QE. It's a proton. Remember, if you see a proton or electron, remember you have information about that on its charge and mass. The electric field is 220 newtons per Coulomb. So that gives me a force of 3.5 times 10 to the minus 17 newtons. And then I need to know its acceleration. That's going to be that force divided by the mass of a proton, which is 1.67 times 10 to the minus, proton is what, 27? I think that's right. Yeah, that's right. And so it has an acceleration of 2.1 times 10 to the 10th meters per second. And I'm looking for the velocity after that time. So v is equal to at. So I multiply that acceleration times that time. So it's going to be 2.1 times 10 to the 4th. It should be. Yeah, 2.1 times 10 to the 4th, or c. It'd be a similar thing. Mainly I want you to understand that when you have a charged particle in a field, it feels a certain force. So this is our A times our time, which is 1 times 10 to the minus 6. To the plus 4th. Let's see. Okay, so no, several steps. Yeah, that's where I got these numbers. So I know the charge of a proton. You might not know off the top of your head, but it's on the equation sheet. It's that E equals 1.6. And then I calculate the force here. And I use that force here divided by the mass to find the acceleration. Newton's second law, right? The mass I get from my equation sheet. This is the mass of your proton. You don't have to know it, but it's back there. And so this gives me the acceleration. And then one more step to find the velocity. I multiply that acceleration times time. A little bit of first semester stuff in here with Newton's second law and that kinematics. Your kinematic stuff, if you have it, I'm not sure that you will, but if you have it, it'll be simple one-step problems like this, but you need to be prepared for that. All right? Yeah. There's, oh yeah. Oh no. Yeah, listen, I'm gonna set it up for you. But the working out of this is hard. Because you gotta solve this equation with these quadratics and stuff. But let me show you how to set it up. Because only one of these answers is reasonable. Is number 4 from the quiz. I had sent an email out about it on the day of or the day before or whatever. But it says this, you have a charge. This is a good question, sort of thinking about how these charges are distributed. A charge Q1 is at y equals 10 centimeters, and another is at y equal -5. So here's my coordinates. I have Q1 up here at 10 centimeters, and it's positive 5.5 nanocoulombs. And then Q2 is at -5 centimeters. This is plus 10 centimeters. -5 centimeters, and this charge is -1 nanocoulomb. And now it's asking me where can you put a Q3 equal to -1 nanocoulombs so that zero force is exerted on it due to the electric field. All right, so I want to know where can I put this third charge somewhere around here so that it has zero forces acting on it. Now, it has to lie along this line somewhere, because if it's over here, it has some charges going in this direction and some charges going in that direction. There is never a place outside of the y-axis where the force it feels will be zero. So now I want to ask myself the question is, where's it going to be? Is it going to be a negative charge somewhere down here, or somewhere up here? And let's imagine what are the forces it would feel. We'll call this one red. If I put a negative charge below the red charge, it's going to feel a force in that direction due to the red charge, and then it's going to feel a very small force due to the positive charge, which is higher up. We've worked questions like this before. It's further away from the big charge, so it feels a small force due to that charge. Now let's think here in the middle, what's going to happen? Well, due to the red charge. You're right. You're right. I was thinking positive charge. Thank you. All of y'all. Y'all are amazing. All right. So, yes, here, that direction. What was the answer? It was A, right? Okay, yes. So, similar argument though. This force is really small because it's farther away from that. Hold on, am I thinking this right? It is 4.8 centimeters. All right, let's look in the middle, guys. Give me a second. We'll look here in the middle. So here, if I have a charge here, I have a force that is down due to this. Oh shoot! I'm sorry. Getting all mixed up now. I have a force that is down. Didn't I just say that? Is this direction because of the positive charge, and it's down due to the -1 nanocoulomb charge. Yeah, they're both up. Why is it 4.8 again? I'm gonna have to come back to you on this. I have to think about this. I thought it was 4.8, but it's looking to me like it should be. Y'all know the question he's talking about? Is it? Yeah. Can I get back to you? Let me think about it. I'll send an email out to level. Okay? It's not working right now. All right. Is that okay, folks? All right. Well, let's go back to that test. Let me make a note for myself. That was number 4. All right, number 11. This one right here. Listen, you will have a 2D vector problem, so make sure you're up on that. All right, so for this figure, what is the magnitude of the electric field at point A? The magnitude of the electric field, I imagine there's a positive particle there, and I say, well, it will feel an attractive force towards there, and a repulsive force towards from the positive 2. And so my net electric field is going to be in this direction. All right, I'm going to call this one E1, and I'll call this one E2. Let me first calculate what E1 should be. It's going to be KQ over R squared, 9 times 10 to the 9th. Q is 1 times 10 to the minus 9, divided by the distance, which is 3 meters squared. That cancels with that cancels with that, and I'm left with 1 Newton per Coulomb. So this is equal to 1, and then I do a similar thing for E2, 9 times 10 to the 9th, 2 times 10 to the minus 9, divided by 3 squared, that's the distance, cancels there, and that's equal to 2. Listen, I'd really look for those cancellations, because if you start putting a bunch of times 10 to the business in your calculator, you're going to make some mistakes. And in fact, I know a lot of you use the times 10 to the caret, Be careful with your parentheses. You got to put that whole scientific notation in parentheses, or sometimes your order of operations will get wonky in your calculator. It's a lot better to use the exponent key. Right, they're nanocoulombs, and nano looks like 9, and it's small, so it's 10 to the minus 9. All right, so that's 2. Now I want to know the magnitude of this vector. So I say the square root of 2 squared plus 1 squared, square root of 5, which is 2.2 newtons per coulomb. And then I also want to know the angle. I think the next question asks this angle. Theta is the inverse tan of opposite over adjacent. That's the y over the x. That's going to be 2 over 1. 63 degrees. Below the positive x-axis. So look for those qualifiers. I'll give them, and you'll certainly see them, but it's below the positive x-axis. Okay? You'll see those. I think most of you are okay at those, but if you're not, make sure that you are, because you'll certainly see them. Anything else? Bruce? I didn't mean to just sort of turn that one off, but... Okay. Yeah, number 6. I feel like an idiot because I can't answer your question. Thanks, Drew. No. Okay, let's see. So, 2 uniform electric fields are superimposed. The first is E1 equals 14 newtons per coulomb. And it says it's in the x direction. I'm going to do a little x hat. That means it's in the x direction. And the other, E2, is 7 newtons per coulomb. And it's in the y direction. I'm going to give a little y hat. With respect to the positive x-axis, at what angle will a positive test charge accelerate in this combined field? So let's draw the field. I have 14 here. I have 7 here, newtons per coulomb. And it wants to know what is the direction of the acceleration. The direction of the acceleration will be in the direction of the force. And the direction of the force will be the direction of the electric field. So really all it's asking for is what is the net, or what is the direction of the net electric field? What is this angle? And so theta is the inverse tan of 7 over 14. Which is 27 degrees. Okay? first question that Drew asked about was kind of a wonky question. Like, I would call that a wonky. It's one that I think you should be able to answer. Obviously, I'm having trouble today, right? But this one is more typical of what you get to go to. Did I just say that? I called it wonky, and earlier I said that you wouldn't have wonky questions. All right? We don't use that word enough, do we? Wonky. Listen, if you ever come up with a nickname for me, are you going to tell me what the nickname is? There's a nickname for various faculty that I know. But if you come up with a nickname for me, tell me, because I want to know what it is. Y'all are nuts. That's what I call you, a nut. All right, what else, y'all? No capacitors. So if you see capacitors, don't include that. Though, please do recognize that sometimes the capacitors and the potential problems get mixed in, like here. So don't just stop if you come to a capacitor problem. Keep working through the old test, but just skip those capacitor problems. You probably see stuff like this, like where is the potential equal to 0? We just did those. Are you okay on those? Looking for opposite charges that are the same distance apart. Of course, you know your units. All right. You want to look at another test, or you have other questions? Sure. So 24. You're definitely going to have one of these. So what is the potential due to multiple point charges? And the potential due to multiple point charges at this point, what you need to know is the distance, 5 meters, because, 3, 4, 5, 5 meters there as well. I want to find the potential due to this charge, which is going to be 9 times 10 to the 9th, kq over r, negative 10 times 10 to the minus 9, divided by 5, plus 9 times 10 to the 9th, times this charge, which is 5 times 10 to the minus 9, divided by 5. And then I cancel out, make your calculations a lot easier. Those cancel and those cancel, so that's just 9. This cancels with that. This cancels and leaves 2 up here, so I get equals to negative 18. Sorry, I know y'all can't see it in the back. That's negative 18 plus 9. Negative 18 plus 9, so my voltage or my potential at point A is negative 9 volts. I'm sorry, I can't scroll up in this document for this PDF. Okay? But make sure you're up on that. We've done that several times, and it's in the homework and old tests and all that jazz, but you'll see it on Monday for sure. Remember too, like if I have, like what if I just told you the potential at a point and I asked you what work is required to bring the charge into that position? Remember we have this expression, work equals Q delta V. So let's say I wanted to move a 2 Coulomb charge from here to over to this position. The work required to do so would be 2 times negative 9, or negative 18 joules. If I moved a 2 Coulomb charge up to this position, it would require negative 18 joules. Negative because you actually, if I was moving a 2 Coulomb charge, I'd have to sort of hold it back, like it would want to go to that position, because it's being attracted to that position because of that big negative charge. Is that clear? Brendan, I think you asked that. Can I clear this? Okay. Yeah, good job. It should be a surprise, but you'll see those. How y'all feeling about this? Slight what? You should be a little bit nervous. I think that's probably healthy for you. Be a little bit afraid, but not too afraid. Like, don't stress over all weekend. Be a little bit nervous because in the past, students have done not so great on this exam. And I want y'all to get a good start. Now, in the past, this class usually does better overall than the one-on-one class. So, that's good news for you. But the first exam is usually sort of a hurdle to get over. and they tend to get a little bit easier. Not for everybody, but they, as a class. Are there any other questions right now? No? You'll have a formal tonight, or a social or something? Try figs, I think, right? You try fig one? All right. That's all. Okay. Auditorium on Monday.